The next topic is called as the momentum integral equations. So the basic idea behind all this, so we have derived a set of differential equation, and then we can solve everything and get all the microscopic quantities. So microscopic quantities meaning we can get u, p, all these things. So all that is fine, but in real engineering designs we are often more worried with pardon me, with quantities such as the wall shear stress, things such as the pressure drop or the lift. So things like this. So we are more interested in averaged quantities. So these quantities are more like derived from these microscopic entities. So but it would be very nice if we can directly obtain expressions for such kinds of things. In particular, we are really interested in the wall shear stress because that is where the ideal flow that is going on outside, the difference between the ideal flow, truly which is ideal flow, which it will not entail any kind of wall shear stress, because shear stress is coming solely because of the presence of viscosity. So this won't be present. So let us see how we can manipulate those equations in order to find such quantities. In particular, we'll focus on the wall shear stress. So let us write down the x momentum equation. So u del x plus v del y is equal to minus 1 upon rho del p del x plus nu del 2u del y2. So this is the equation that we had. So this is the x momentum equation. Let us now integrate the x momentum equation inside the boundary layer. So if this is delta, let us integrate it over the boundary layer. Essentially, you are doing a depth average. Okay, essentially. So we will integrate this. So integral u del x dy going from 0 to delta. So delta is a function of x, obviously. So delta is a function of x. I'm not gonna verbatim express it over here. Plus integral v del u del y dy going from 0 to delta is equal to minus 1 upon rho del p del x. Okay, integral 0 to delta dy plus nu integral del 2u del y2 dy going from 0 to delta. Okay, so let us simplify this particular term. So let this be the first term and this be the second term. So it becomes v u evaluated at 0 and delta minus integral. So if this is the first function, so del v del y and integration of this, so u and then dy, so 0 to delta. Okay, now we can make use of the continuity equation to represent del v del y as minus del u del x. So using these particular terms, so this is v times u going from 0 to delta, no problem, but this entire term will become plus integral 0 to delta u del x dy. So finally you see that this particular term and this particular term are equal. So the left hand side simplifies to vu 0 delta plus twice integral 0 to delta u del x dy. This is equal to minus integral 1 upon rho del p del x dy plus nu. So what will this term be? It will be simply del u del y evaluated at 0 and delta. Okay. So what is this term going to be? Okay, so let us see how we can simplify it. So we can write it as v delta times, so u at delta will be equal to u infinity minus v at 0 will be 0 and u at 0 is also 0. So let's not write this negative term. So this will be plus twice integral of 0 to delta u del u del x dy, and this is equal to minus integral 0 to delta 1 upon rho del p del x dy plus mu del u del y at delta. So when we are at the edge of the boundary layer, the whole premise was that the velocity profile does not change. So the after this point, so at delta there is no more change, so this simply will reduce to minus nu del u del y at 0. Okay, so now what we want to do is to somehow cast v infinity in terms of del u del x. So let us again write down the continuity equation. So now let us integrate this equation from 0 to y, 0 to delta. So this implies integral 0 to delta del u del x dy plus integral 0 to delta del v del y dy is equal to 0. So what is this term going to be? It's simply going to be, the second term is simply going to be v at delta minus v at 0, and v at 0 is equal to 0. So this term vanishes. So then we have an estimate for v delta. See, I don't want to keep v delta over here because v delta is not known. What I can benefit from is expressing everything in terms of u. So v delta becomes minus integral 0 to delta del u del x dy. So I can substitute this expression over here. So this becomes minus u infinity integral 0 to delta del u del x dy plus twice integral 0 to delta u del u del x dy is equal to minus 1 upon rho integral del p del x dy minus nu del u del y at y equal to 0. Okay, so far we have obtained a great deal of simplifications, and now this particular term is equivalently 1 by rho integral dp dx at dy. So this goes from 0 to delta, and the reason being the y momentum equation causes this equation to be independent of the y coordinate. It is dependent only on the x direction. So now let us look at the free stream equation. So because everything is imposed on the boundary layer, the pressure is imposed on the boundary layer, we can go back to the governing equation for the Euler equation. So 0 is equal to, or not 0, u du infinity dx, u infinity is equal to minus 1 upon rho dp dx. So keep in mind that this is written for an ideal flow which is unidirectional. Okay, so it can vary in x, but the ideal flow that is outside the boundary layer is unidirectional. If it is not unidirectional, that would lead to a v infinity component as well. But we are taking this unidirectional. So this particular term can simplify to what? So this will become 0 to infinity u infinity du infinity dx dy. Okay, so finally let us take this particular term on the other side, or in fact let us take this on the other side and take everything else on this side. So we have mu by rho del u del y at y equal to 0 is equal to integral 0 to delta u infinity du infinity dx dy, this term, plus integral of u infinity, so this particular term, del u del x dy minus twice integral u del u del x dy, 0 delta 0 delta. Yes, better to not draw them like TikTok icons. No one likes those. Okay, so mu del u del y at y equal to 0 is tau wall. So tau wall upon rho is equal to integral 0 to delta u infinity du infinity dx plus u infinity del u del x plus rather minus 2u del u del x. So this is what we have so far. So now we can simplify this further actually. Let us combine certain terms. So this can be written as 0 to delta. So this particular term is going to be ddx of half u infinity square. This particular term is going to be del x of u infinity u minus u du infinity dx, while this particular term is also going to be minus 2u. So yeah, let us keep it like this. In fact, So I've combined, I've kept this term as it is. I've kept it as it is. So this term is this term. This particular term is this particular term. U infinity this. And this 2 cancels out. So this particular term is combination of this particular term and this particular term. Well, there is nothing sacrosanct about this also, and the fact of the matter is we want to cast it in a better form, and the reason we want to cast it in a better form will become clear later on. Okay, so the simplification of this expression, so this is still tau wall upon rho, is in the form of two integrals. It is in the form of two integrals. So the first integral looks something like this. So essentially it's like some difference in a quadratic form of velocity. Second expression is also some difference in a linear form of velocity. So this reduces to further, we can, I mean not reduces to, but this can be simplified to something like this. Del x of u infinity minus u dy plus du infinity dx integral 0 to delta u infinity minus u dy. So what have we gained by writing it like this? The one major thing that we have gained is, see, beyond the boundary layer, so as y becomes larger than delta, u becomes equal to u infinity. Okay, so u tends to u infinity, so all these integrals will vanish. So beyond y equal to delta, these integrals will vanish, so I can conveniently replace the limit 0 to delta as 0 to infinity. So this becomes tau wall upon rho is equal to 0 to infinity del x of u infinity minus u dy plus du infinity dx integral 0 to delta u in not 0 to delta, this is 0 to infinity u infinity minus u dy. So we have replaced everything by an infinite integral. Okay, so this is one very important equation. Now in what follows we will discuss two important ideas. One is the displacement thickness and one is the momentum thickness.